Welcome to this explainer. Today, we're tackling something every robotics developer has fought with: flaky wall clock tests and messy sim-to-real transitions. We are going to map out a beautifully deterministic ROS2 and MuJoCo software-in-the-loop architecture that actually cures this chaos. Let's get right into the rules that keep this system stable.
All right, here is our agenda. We'll build this from the inside out. First, the single data loop. Second, the HAL boundary. Third, deterministic simulation time. And finally, number 4, 6 architecture decisions.
Section 1, the single data loop. We are starting right at the beating heart of the robot.
Because, when you strip everything away, this entire complex project is ultimately just one continuous control loop. The step-by-step flow here is everything. It kicks off with a navigation node publishing a twist command. Next, the kinematics layer converts those target velocities into specific wheel velocities. Then our hardware abstraction layer, the HAL, writes those directly into MuJoCo. We hit the MJ step command to advance the physics world, and boom, sensor data flows right back to navigation so it can recompute. Literally, every architectural choice we're looking at today exists for one reason: to keep this specific loop honest, whether it's running on your slick developer laptop or some random CI runner in the cloud. That consistency is the absolute holy grail.
Okay, moving on to Section 2, the HAL boundary.
So, how do we protect that vital data loop? With the HAL. This handles our sim-to-real transition in one neat little box. We use a single abstract class, Robot Hardware Interface, which is essentially the ironclad contract between the ROS world up top and the physics world down below. Right now, MuJoCo Interface is our active implementation for simulation, while CAN bus Interface is literally just a stub, sitting there waiting for real motors. Sim-to-real in this architecture is just swapping out this one box. The entire stack above it, the kinematics, the navigation, all your tests, stays byte identical.
But to make that swap actually work flawlessly, we have an absolute non-negotiable law here. Hard rule number 4, MuJoCo types are confined to a single .cpp file. The header file only forward declares MuJoCo elements as opaque pointers. That means nothing above the HAL even knows MuJoCo exists. All they see are generic wheel commands, wheel states, IMU samples, and range scans.
Like the quote says, this abstraction isn't cosmetic. It is the load-bearing wall of the whole project. Think about it. If swapping to real hardware forces you to tweak your navigation code, your HAL completely failed. And actually, this is exactly why they made a documented timebox choice here to build this custom thin HAL, instead of just pulling in the standard ROS2_control. Choosing speed to CI right now gives them a contract tuned specifically to this robot, while keeping a migration to ROS2_control as a documented stretch path for later.
All right, Section 3, deterministic simulation time.
This is where we kill the flaky tests for good. In CI, there is no wall clock, period. Our MuJoCo bridge is the absolute sim time authority. It owns and publishes to the /clock topic. Every single other node in the system is commanded to consume this clock by running with the parameter useSimTime set to true. So time only advances exactly as fast as the physics step is called. Got a beefy machine? You'll process 100 Hz of sim time per 100 Hz of wall time. Stuck on a slow, loaded CI runner, it is still exactly 100 Hz of sim time, it just gets delivered a little slower. This is a total game changer when you compare a dev laptop to a shared CI runner. GitHub Actions runners have completely unpredictable CPU resources. Sometimes they're snappy, sometimes they're sharing a throttled virtual CPU. If you write a test asserting the robot reaches the goal in 5 seconds based on wall time, it is going to fail intermittently, usually on a Friday afternoon when you're just trying to merge. But against sim time, 5 seconds means 5 seconds of actual deterministic simulation every single time. It completely ignores host CPU speed. Now, there is one really subtle exception here that will absolutely bite you if you're not careful. The bridge that produces the /clock cannot consume it. If you ran the bridge with useSim_time set to true, it would just sit there waiting for a clock message that it is supposed to publish itself. Classic deadlock. So the bridge has to run in wall time, driven by a timer at 100 Hz, to execute the physics loop and publish the clock, so that everything else can safely live in sim time. And because the system relies so heavily on this deterministic clock, here is another hard architectural law. Absolutely no sleep commands in your tests, period. Calling a standard sleep function instantly couples your test right back to wall clock speed, which resurrects the exact flakiness sim time was meant to destroy. You have to use conditional waits only. Spin until a future is complete,
or run a predicate loop against SimTime.
Let's bring it all together in Section 4, 6 architecture decisions.
Good architecture is really just about documenting time-boxed choices. This table shows our 6 architectural decision records, or ADRs. These act as the rulebook to scale the system. We just talked about the custom HAL and the single SIM clock, but notice that all of these decisions are reversible, and more importantly, they're all written down so the why is always just one search away. Let's drill into a few of these that directly impact developer workflow.
ADR 1 ensures we use a single binary for both our dev screens and CI. Since the MuJoCo physics step has 0 OpenGL dependency, we just use a runtime flag, GUI equals false, to run headless in CI. We never use messy compiler directives like if-def headless, avoiding divergent binaries and upholding the rule to always test what you ship. Then there's ADR 3, which tackles GitHub runners randomly blocking multicast discovery. It gives us a layered data distribution service, or DDS fallback. It starts with a simple environment variable, ROS_localhost only equals 1. That works about 95% of the time, and we keep a manual unicast XML profile ready as a backup if the network policy suddenly flips.
Next up, ADR 5 manages our multi-stage Docker builds to keep image sizes small, but it enforces a strict rule: source, not exec, in the Docker entry point script. If you use exec on a ROS setup bash file, your environment variables vanish into the child process, giving you a command not found error and totally wasting a CI cycle. Finally, ADR 6 solves that classic integration nightmare where 2 pull requests pass in isolation but break the build when combined. By using GitHub's native merge queue, every single PR gets automatically retested against the latest main branch before merging. It acts like an automated integration engineer that never sleeps, structurally guaranteeing that it passed on my branch but broke on main simply cannot happen.
When we map all these rules onto our package layout, the segregation of duties is super clear. The description package holds the robot model, the bridge holds the HAL boundary, and nav holds the controllers. But what you should really take away from this is the autonav_control package. Notice how it deliberately has 0 ROS dependencies? It's pure math, just converting twists to wheel velocities. That absolute purity means developers can unit test it with insane speed and reliability, using a plain test binary. No nodes, no DDS, just instant feedback. So, we've built this bulletproof theoretical skeleton today, from an isolated data loop to a rigid HAL to the deterministic clock and our documented architectural rules. But this leaves us with one massive, provocative question. How does the concrete YAML of our CI/CD pipeline actually enforce all these abstract promises without failing? What does that exact sequence of jobs look like to turn a code push into a green check? Well, that is exactly what we are going to have to uncover next time. Thank you so much for learning with us.